Hello class, this is Adam Ward. I wanted to follow up on one of the last topics we covered in our study of flow through pipes that are flowing full, pipes in parallel and pipes in series. Just to remind you, for pipes in parallel, as we've got shown in this exercise, the head loss through each of the two or however many pipes will be equal, the pressure drop across them. For pipes in series, for example, if you had a third position you were interested in as shown in orange, the flow through both of those is the same, but the head loss in pipe 2 and in pipe 3 may be different. And in this problem, recognizing that we're given the pipe geometry and something about the fluid, and we're asked to find the distribution of flows, this should look familiar to you from class as a Moody diagram problem that may require iteration. So, we're going to approach this problem by recognizing the head loss in each of the conduits is equal to one another. And throughout the problem, I'll use green to represent the head loss and all of the parameters for A, and I'll use this darker red color to represent pipe B. So we know the equation for major losses, our friction factor times length over diameter times V squared over 2G. Set those equal. And recognizing that velocity is equal to discharge over area, we can substitute in Q squared over A squared for that velocity squared term. So I'll make that substitution here. And at this point, we're ready to start trying to put some numbers to the problem. We're given a roughness height of 0.26 millimeters, and so I'll calculate that relative roughness height for the Moody diagram for both of pipe A and pipe B as shown here. We'll take that to the Moody diagram, and this is the type of problem setup in which we're going to need to guess a Reynolds number, guess a friction factor, solve the problem, and then check and iterate as necessary. Now my suggestion to you is going to be to guess a high Reynolds number. That's the right-hand side of this plot. That's where the lines are more or less horizontal. And we'll do that because it gives us the widest range of possible Reynolds numbers for which this friction factor will still be valid. So for segment A, I calculate a friction factor of about 0.024, and for pipe segment B, a friction factor of 0.03. And so again, I wanted to just highlight in the red box here that large range of Reynolds numbers for which these values are approximately constant. So using those values in the equation that we'd written above, we can go ahead and plug in all of the information that we're given in this problem. And you'll notice I ran out of room, so I'm squeezing that cross-sectional area term onto an extra line written in red. And at this point, you look at the problem and perhaps you're feeling like we're in a bit of trouble. You've got two unknowns, discharge in A and discharge in B, and thus far only one equation. But we can remember that by conservation of mass, the flow through the pipe at point 1, in this case 1 cubic meter per second that we're given, has to equal the flow in pipe A plus the flow in pipe B. So from there we've got two equations, two unknowns. This becomes a tractable problem, and we can solve for the discharge in A and the discharge in B as shown here. Now it's tempting at this point to think that you're done and simply box your answer. As a reminder, we had to guess a Reynolds number in order to get an F in order to get the discharges. And so at this point, this becomes a major losses problem in which you would have to, using these discharges, calculate the Reynolds number in pipe A and pipe B, go back to the Moody diagram, and check those friction factors. If they match what we guessed, you're done. If they don't, we'll need to iterate through the problem at least one more time. For students who are looking for a bit of additional practice, one extension to this problem is to consider what happens between pipe 2 and point 3 shown on the diagram. And so if you assume that you have 500 meters of flow through the smaller diameter pipe at point 2, and let's assume that has a diameter of 0.5 meter, and then through pipe 3, where we could assume that it has a diameter of 1 meter, the question would be to find the total head loss from pipe 2 through segment 2 and 3, or between the 2 points that are shown here. That's an extension of the problem, and it will allow you to practice with pipes in series as well as pipes in parallel. I hope you find this helpful. Thank you.